the idea is this is a vector that we want to wipe out completely, except for, actually it's not j plus 1, it's j to m. J plus 1 to m is what we want to get rid of. But we use, so this vector contains everything from the diagonal on down in column J. So everything below this JJ entry, we're going to wipe out. Okay, so this house function computes in an efficient way the vector v for the household reflection. And then, for convenience, actually I think the way house works is it returns actually not the same v we've been talking about here, but a convenient multiple of v. So this v is not necessarily a unit vector. So what I do for convenience is I set a constant c equal to 2 for the household reflection, divided by v transpose v. So that makes sure it's normalized. Okay, so so here we use the code in house.m. Okay, so now we can actually perform two household reflections. I'm going to perform a household reflection on the left of R to keep wiping out entries. But then I'm going to apply it on the right of Q to keep updating Q. So it's just like with givens. You zero from the left, you update Q from the right. There's no difference there. So to apply a household reflection on the left, I'm working on rows j to the bottom and columns j to the right. So I'm working on just that portion of a matrix. So I'm working on a smaller and smaller portion of a matrix as I proceed. So I take that part itself. So this is like the identity part of the household reflection, minus c, this constant c, times v times v transpose times that same portion of R. Okay. So this zeroes out the appropriate elements in column J, but then it has to update everything in the subsequent columns. Then I update Q, and for that I'm updating all rows. And let's see, in this case, since I'm applying this on the right, it's going to just be columns J through M, M rather. It's going to be M because Q, R is an M by N matrix. Q, on the other hand, is M by M. Okay, so I have, so what's happening here is I have Q minus C times, I'll dispense with the stars here, I don't really need them. So then I have Q times V transpose. Now, one thing that's important here as far as coding goes, you want to make sure to use parentheses appropriately to make clear to MATLAB or Octave, whatever you're using, to perform the multiplications in a most efficient way, because you don't want it to form full matrices and perform matrix multiplication. You only want it to do matrix vector multiplication. So up here, put parentheses around this. So here it's going to do a vector times a matrix as vector matrix multiplication, and then it'll do this outer product. But an outer product is fine, because that's only order n squared operations instead of n cubed. Here too, have it group these, so it's matrix vector multiplication and then an outer product. And that's the whole algorithm. So unlike a Gibbons rotation that it zeroes one entry at a time, household reflections are really destructive. So they wipe out almost entire columns at a time. So they both have their uses. It depends on what you're trying to do. So now we have two efficient ways of computing the QR factorization that are both quite numerically stable and quite efficient. There's also Graham-Schmidt orthogonalization, which is inferior to both. So I won't bother discussing that. Now, as far as choosing between Householder and Gibbons, one advantage of Gibbons is you're only rotating 2 rows at a time. When I described the algorithm, I ordered these rotations in a particular way, but you don't have to order them that way. You can take 2 disjoint sets of rows and rotate them, and that means you can apply Gibbons rotations in parallel. So if you have parallel architecture, you can get at least some speed up that way. And as we mentioned earlier, Gibbons rotations are better for updating the QR factorization. Like, for instance, suppose you add a row or column to the matrix and you want to update the QR factorization instead of recomputing it from scratch. Gibbons are more versatile for that sort of thing than householder reflections are. However, so based on what I discussed on Monday, we now see how to compute a QR factorization that's later used in order to solve the least squares problem, which in turn is used in some iterative methods that I'll be covering next week. So, a very complex picture put together here. However, both householder and Gibbons transformations are going to be very important to us after I get through all the iterative methods, because then we're going to look at how to compute eigenvalues and singular values. Both are essential tools for that. So these will come back to haunt us, or just you. Okay, so I have to fix the notes and make sure that this code I've advertised is actually on the site. So back to iterative methods after